Hello, my friends. In this video, we are going to talk about Gauss's law. At this stage, I don't think it's a good idea to derive everything. Uh, but instead of deriving the original formula, I think it's better to talk about how to use the formula because the formula for Gauss's law is so simple. The area integral of a closed surface of an electric field is going to be equal to charge divided by the charge density. And the charge is the charge enclosed inside the integral. So let's say you have a point charge here. Uh, let's say we have a point charge. Q. Uh, so this is the point charge Q, and you are going to measure the electric field at a distance. Say the distance is A. Uh, A away from the charge source. So you are going to measure the distance, the electric field at this point. And the distance here is A. So how are we going to solve it? The idea is very elegant for Gauss's law. And by Gauss's law, the area of a closed surface. This means you have to invent a Gaussian enclosure to solve this problem. So for a point charge, we can invent a Gaussian enclosure as a sphere of equal radius everywhere. So this is the thing what we can do. The radius is A. So what is the total surface area? The total surface, yeah, let's say, right, we are going to substitute the parameter into the original formula. So in this case, we have the area integral of a surface. This is a the surface is actually a total surface of a perfect sphere, and E and dA, and the point charge is Q, and then divided by epsilon. And in this case, the electric field is going to be the same everywhere. The electric field here is going to be the same as the electric field here. It's going to be, which is equal to be the electric field free. So in other words, electric field 1 is equal to electric field 2 in terms of magnitude. Electric field. So in this case, we can just simply use the scalar form of the expression, and then dA E, and this E is the same everywhere. We take this out of the integral. And the total surface, the integral of the total surface area, which is the total surface area of the sphere. The sphere's area is 4 pi A. So that's why, 4 pi a square. Okay? So that's why we can simplify this uh, equation uh, into 4 pi a square uh, and then q divided by epsilon. And if it is the case, then there is no reason why you cannot further simplify it. In this case, the electric field will be equals to Q and then 4 pi a square and epsilon, which is exactly the same as Coulomb law. Uh, Coulomb law is also in this form. So here we have managed to use Gauss's law to prove the original Coulomb law. And let's take a look at one more example. And let's say we have a long wire. We have an infinity long wire uh, of charge density lambda, of charge density lambda. And we are going to find out the electric field. So the wire is going to be in this form and it's going to be very long. I'm going to pretend it is a long wire. And we are going to do the same. And suppose we are going to use the tester to detect the electric field at some points. Say the point that we are interested in is H. And we are going to detect the electric field here. So we don't know the length of the wire, but we know it's very long. So what we are going to do, what should we do? Let's say this electric field is EY. Yeah, it's important to understand that the electric field can be pointing to all directions. Uh, Now, in this case, how are we going to use Gauss's law to solve the problem? My suggestion is we imagine there is an Gaussian enclosure, and this Gaussian enclosure is a cylinder. So you have a Gaussian enclosure here. Uh, this is the end of the wire. Uh, and let's say this is charge density. Right? Let's write down. And we have already, yeah, let us say it again. Charge density lambda. And we are going to have the same treatment here. And this time, right? And so basically it's a three-dimensional picture. And we imagine uh, we have a Gaussian enclosure. So this one is so-called Gaussian enclosure. Gaussian enclosure. And we are going to apply Gauss's law to solve the problem. the so how are we going to do it? So first of all, in this Gaussian enclosure, which is a cylinder, we have three surfaces. The first surface is S1, and we have the lateral surface, uh, which is a flat surface, right? Say this is S2, and we have the same in S3. So in fairness, you need to find the electric field all over this closed surface of this Gaussian enclosure. Now, uh, my suggestion is we use uh, um, uh, by applying Gauss's law, uh, um, we have the closed surface, and the closed surface here is going to be um, dA. Uh, sorry, I write it down again. Uh, then we have free surface. Yeah, let's break down the expression here. We have free surface. So one is the S1, the other is S2. So let's say EY, and this one is S1, and dA here. So it's going to be a vector, and then the other two surface, S2, and let's say you have a electric field component here, and the electric field is going to be EX. The vertical is Y, the horizontal is VX. So EX, and we have EX here, and the A, the area, and we are going to have the same thing. EX and dA. And on the left side of the equation should be, the right side of the equation should be total Q. The total Q is going to be the charge density multiplied by the length of this wire. So the length here is L, so it's going to be epsilon. Now, before going on further, let's examine the nature of this horizontal component of the electric field. Assuming that the EX, the testing point is right at the middle of this wire. And in fairness, the electric field pointing this way should have the same magnitude as the electric field pointing to the left direction. The direction may be opposite, but the magnitude should be the same if the wire here is symmetrical. So it's fair to say that this term and this term are cancel off with each other. So what we have left is just this term. So we have this term here. And now, let's examine what is this term, what this term is. And you have the electric field vector here, and times the area. And the electric field is going to be the same everywhere on the surface on the lateral surface of this cylinder. Or at least this is our assumption. So this integral should be resolved into EY. In this case, EY stands for the magnitude of the vector EY here. And again, right, we end up with S1 and BA here. And now we are now looking for the area. What is this area? The area here should be the circumference of this circle times the total length. The circumference of these circles here is 2 pi h. Two pi h. And what is the length? The length is L. And we are going to close the equation by writing the right side as well. So hang on a minute. Now lambda L divided by epsilon. You have L in both sides of the equation. You have L here and you have L here. So it's better to cancel off with each other. So finally, we end up with only this expression, right? And we can safely conclude that EY, which is the electric field in the vertical direction, is equal to lambda divided by 2 pi h epsilon. So this is going to be our answer. And if you have any questions, please leave your question to the comment section of this video. Thank you very much for your time and see you later.